So one of the variation in gradient descent is gradient descent with momentum. So in gradient descent, momentum meaning is taken in its literal meaning, like when we give a momentum to something, then its speed increases. So momentum here in GD is being used in the same meaning. For example, let's say if this is a hill and this is the bottom of the hill and this is somewhat elevated area and a ball is rolling down the hill, so if the size of the ball is increasing, so what will happen, so as it will reach this bottom, so because of its increased size it will have a more momentum, meaning more velocity, and because of that velocity and that momentum it will have the ability, or there will be a possibility that it will move on and escape from this bottom. So here in GD with momentum algorithm, momentum is given to the gradient descent algorithm in a specific way, and that specific way is given here. For the weight update, we use previous weight minus this VT term, and this VT term is calculated in this way, which uses the current gradient and the previous value of Vt or velocity. Um, this is further elaborated here. So if we look at here, how to calculate this Vt. So remember that this Vt it actually calculates momentum for this weight update expression. So here if we elaborate or expand it here, if we want to calculate V1, then V1 contains gradient descent. V1 means at iteration 1 it will include gradient at iteration 1. So V0 is normally you can set it to 0. So you can think about this one V1 as the only gradient value multiplied by the learning rate. Now comes V2. So V2 is calculated like this one. Now V2 contains the previous gradient that was calculated at V1 at iteration 1 plus now the new gradient at iteration 2. So what does that mean? So V2 is actually accumulating gradients, previous gradients and with the current gradient. Now look at V3 at iteration 3. What happens? This V3 contains gradient, previous gradient, then gradient in the second iteration, and then the current gradient in third iteration. So now V3 is actually summing or adding up all the previous gradients with the current gradient. So whenever we have to calculate this weight, W2, and let's say at iteration 2, so it is updating weight by W1 minus the gradient value, which is Vt. Now let's see at W3, at V3, at third iteration, W is updating itself the old value of weight minus this one. What does that mean? So that to update the weight value, it is using previous gradients. Again, you see at fourth iteration, to update weight value at fourth iteration, it is using sum of the previous gradient. So in this way, this sum of gradients, it actually gives a momentum effect to this W, to this weight update expression. And because of that, this momentum value, we can see the effect of this one. Because the surface of a function that we want to minimize that function, so it can have, different minima. For example, if we extend this one, this is one local minima, this is you can say another minima. So one minimum, the second minimum. So the better way is that if we minimize function, so that function should go to this point. So the minimum point will be at this function. So If we are updating our weight values with the help of gradient descent with momentum, then what will happen? It will add momentum to the algorithm, and the algorithm will not trap at this local minima. Rather, because of the momentum, it will come out from this one, and there is a high likelihood that it will settle down this at this point, which is the global minima of this surface or of this function. So this is the benefit of momentum gradient descent.